Hello, everyone. This is Spencer Snowling from Hydromantis, and as usual, I'm very happy that you could join us today for the monthly GPSX webinar. Um, so I'm joining you from my house, from a storage room off of my kitchen, as I'm sure many of you are also joining from your house. So I'm glad that you're able to make it. I hope that you're doing well, staying healthy, and everything is going okay in this um, strange and stressful time. But I'm glad that we have the technology to be able to get together like we always would normally do around this time of the month, to be able to talk about modeling and so on. So I'd like to take the opportunity to just say a few words about Hydromantis and what we're doing right now with respect to the COVID-19 lockdown. So first of all, the one thing you need to know is, of course, that Hydromantis is basically just carrying on as normal, except for the fact that we're all working at home. Here's a selfie of me that I took yesterday at my little workstation here, just off the kitchen, in my storage area with a window, and the squirrels keep coming to look at me and so on. But anyway, I'm glad that we're able to be able to keep moving along. So as normal, you can continue to send any questions that you might have if you have technical support that you'd like to get some help with. As usual, support at hydromantis.com is the place to go. And I'll just remind you, in case you haven't already been doing this, when you want to send us a question about something that's going on in your GPSX layout, while you have the model open in GPSX, go to the File and the Archive command, and that will create a zip file for you. And then you can attach that to your email, and then that way we can take a look at your layout right away. So things are carrying along. We're actually quite busy. I think given the amount of tech support questions that have been coming in lately over the past couple of weeks, I think there are a lot of people out there doing modeling right now because it is something that's transportable and you're able to do it at home. So we're going to continue to run our regular, usually monthly webinars like this one, plus probably some additional things. So I'll just ask you to keep an eye on your email. We may be sending out a few things to talk about some extra stuff that we'll be doing over the coming weeks. Now, if you are working from home and you do find that you're struggling with connecting to a network license of GPSX, for example, through a virtual private network or whatever it is that your company has you set up to do, if there is something that's not working out for you, we can provide you with a solution, whatever you need to be able to get around that. We have done that for several clients where we have provided some temporary licenses for their employees. So basically, if you're struggling, let us know. We'll work out something for you. Okay, so on with the regular webinar. So today we're going to be talking about modeling clarifiers and settlers in GPSX, and there are lots and lots and lots of options when it comes to this very important part of the activated sludge process. And so we wanted to talk to you in detail. This will be a slightly longer webinar than normal because we wanted to get through all of the stuff that we have available. As per usual, it's not even long enough to talk about all the stuff that's in GPSX, but we're going to try to hit on all the highlights anyway. So we have several different types of clarifier models, and I'll go through those. We're going to be looking at how those models differ from each other. We're going to talk about the one that is probably the one that everybody uses the most, the one-dimensional flux model with the settling parameters and so on. I'll talk about the important parameters to keep in mind when you're setting up a clarifier in your GPSX layout, and then various display and data visualization methods that we have for plotting the output from your model. And as usual, a couple of desktop demonstrations. And also, as usual, we'll do a few questions and answers at the end of the webinar. So as if you've been to our webinars before, you may be familiar with the GoToWebinar dashboard. At the bottom of that, you will find a questions box. You can type your questions in there. Go ahead and type them in as we go along, and then they'll collect it all up for me. And then at the end, we'll take a look and answer as many questions as we can at the end of the webinar. Okay, so as far as clarifier models go, the ones that you would typically be using on a regular basis, there's sort of four of them, the objects in GPSX that you'll probably end up using on a regular basis. are circular and rectangular primary clarifiers, and then the secondary versions of those two as well. So the primary ones are the green ones and the secondary ones are the blue ones. And you can grab those from the appropriate panels on the left-hand side of your drawing board in the primary treatment and in the secondary clarifiers sections, and you can drag them and put them on the board. So a couple of people have asked me recently, what's the difference between those two models? They are almost exactly the same. It's somewhat there to help with the aesthetics of your layout, to make it look proper so that it matches what you're looking at in reality. There's some slight differences in the way you could input your information, but for the most part, it's underlying, it's pretty much the same model. There is one other model too, the gravity sludge thickener, which is part of the biosolids treatment. So it's basically, again, the same settling model, but with different default values. And so that's also available in the biosolids treatment section, second from the top up here. So when you put one of those on your drawing board and right-click on that object and select the Models menu, you will be able to see that we have several different choices of model available for you to pick from. In most cases, the simple 1D one will be the default that has already been selected for you. But you can select any one of those, and they have sort of different degrees of complexity and different purposes. So this chart here describes the basics of what is the difference between all of them. So the first three that are listed here at the top, the point model, the empiric model, and then these ones here that are based on things like SOR and SLR. These are zero volume settlers. And what we mean by that is there is no hydraulic mixing, there's no hydraulic lag, so to speak, in this model. Everything that flows in immediately flows out, but it does undergo, obviously, the solid settling portion of that. But we assume it's a zero volume settler. So the other two that are there, the simple 1D model used to be called the no react 1D model, and the Mantis 2 reactive clarifier model. Those ones, the hydraulics there are actually modeled with some degree of sophistication. So it is a model that has volume, and you set the shape of the clarifier and its volume, its surface area, and depth, and so on. And so therefore, it's not an instantaneous pass through like the other ones are. And so each of these has different levels of complexity, and I'm going to go through those right now in a little bit more detail. So we'll start with the point clarifier model. So basically, this is a perfect settler model. That's really what this is about. This is all of the solids are going to be removed no matter what. There's really only one operational parameter to set, which is what is my underflow flow rate, and all the solids will go down there, and the effluent from this particular clarifier will have, by definition, zero solids in it. So it's perfect settler, and it can be useful for design purposes and so on. The empiric clarifier model is more or less the same thing, except that instead of it being perfect, 100% removal of solids, you can actually define the removal efficiency on a percentage on concentration basis. So there are three parameters that you can use to set that. There's the underflow rate, the underflow solids concentration, and the removal efficiency. So basically you pick two of those and then we'll calculate the third one. I typically recommend using the underflow rate and removal efficiency option. That's the one that tends to fit most of the time with the kind of data that you're going to typically have. If by chance you use underflow rate and underflow solids concentration, you are actually fixing the mass flow rate by doing that. And that might not be quite what would sort of typically be realistic in reality. So in this case, like the default is set up there, removal efficiency and underflow rate are usually the ones that we like to do. Now, this is available in the secondary clarifiers and in the primaries. And in the primary, we actually have one other one as well, called one option inside that empiric model called use solids removal efficiency model. And in that case, the solids efficiency capture rate is not set by you, but rather from a very empirical model that's available. This is actually something right out of the Metcalfe and Eddy textbook that has a couple of parameters there. It's essentially a regression from some data, and but it's something that is a little bit sensitive to the amount of flow going through that unit. So they're very good. Those point and empiric models are very good for when you want to do a very quick setup of your model, and when you don't really need an overly predictive model of your clarifier performance. So this is handy if you're doing typically design work where I want to be able to just focus on the biological part of the system. I want the model to do the solid separation so that I can recycle my biomass back and get all of that aspect of it done correctly. But I don't want to have to mess around with settling parameters and so on. I really would just want it to do its job all the time, and then I'm going to focus on getting my BNR sorted out the way I want. So it's not a predictive model because you're specifying a % removal that happens all the time. So it will, the clarifiers themselves will never fail. Excuse me, but these kind of empiric models are actually quite handy for doing that kind of work. Okay, so next, stepping up in the level of complexity, we have those two really simple models. Now in the middle, we have these ones, WEF TSS SOR, which is in the primary clarifier object, and the TSS SOR SLR, which is in the secondary model. Secondary clarifier object. So these are ones that are basically, yet again, an empirical model. So again, you're going to ultimately be removing a % of the solids on a concentration basis. But rather than setting that % removal, it's going to be calculated as a function of some loading parameters. So the ones that you see in the title of the model. So this one, WEF TSS SOR, it's using surface overflow rate and solids concentration as a way to define what is the % capture. And so this is taken actually from a WRF research report. The other one is one that we've developed in-house through a very similar type of experience. It's actually calibrated to work somewhat as closely as possible to what our simple 1D model does, except it's a very empirical one. So it's nice and easy to use. It solves really quickly as far as model speed goes and so on. So these are used for making rough estimations of clarifier performance. So they're dynamic in the sense that they'll actually respond to changes to the loading and to the flow rate. Again, they're used in places where we want the model to be somewhat realistic to have some response to it. But I don't want to go through the whole process of actually calibrating all the settling parameters and so on. So this is kind of our median, in the middle, the median kind of level of complexity. Okay, so now we'll move on to the most complex version, which is the simple 1D model. So this is now a full mechanistic dynamic model of solid separation where we're going to divide the clarifier into 10 layers, and then we are going to calculate the mass balance around each of those layers and therefore be able to solve the model for a concentration in each one of those horizontal layers in the clarifier. And so this is the one that is probably the most realistic of all the ones we have, in the sense that it can give you a solids profile in the clarifier, and it's dynamic, so you'll see loading changes when we increase the flow rate or we change the settling parameters and so on. Now, it requires quite a lot more information and often calibration of those settling parameters in order to match it to the data that you have. So if you can imagine a vertical cross-section of your one-dimensional settler model. And if you imagine that to actually be broken into 10 layers like this, and we by default use 10 layers because most of the settling parameters that we have in our models are calibrated with it using 10 layers, so it will look like this. And then we have the flow, we have a feed layer where all of the solids and the flow that's coming into the clarifier are sent into a particular feed layer. You can specify what that is. We then are feeding in the flow with all of the solids in it into that, so it'll be typically mixed liquor coming in. We are, of course, withdrawing flow off of the bottom for our recycled activated sludge, and it's going to come off and take the solids away at that predicted concentration. There's also going to be some wastage. That's, of course, the lower right-hand connection point on the model. And then there's the overflow connection point, which is where all of the hopefully very low solids will be leaving the system and going on downstream. So let's take a look at this in a little bit more detail. So I kind of expanded that out, and we've got our 10 layers there. And as you can see, we've got our flow coming into that feed layer. Now, in this one-dimensional flux model, the reason it is a really good predictor of the behavior of this type of system is that we're actually doing a mass balance around every one of these layers. So each one of these things is sort of its own completely mixed reactor in a way. So this very flat pancake-like horizontal layer here, number 3, is going to have the same concentration all the way from one side to the other. But it will, of course, be ultimately a different concentration than the ones above it and the ones below it. And it's those concentrations that we're solving for while the model is running. So what happens is those solids come into that feed layer, and there's two main things that are going on. One is the liquid flow that's going through that system. So we have flow that's coming in, it's entering into the clarifier, and then it's splitting, and some of it is going out the top as part of the effluent, some of it is going through the bottom and becoming part of the RAS, and some of it is being wasted, and then it's coming back around again in the mixed liquor. So the flow, as it moves here, and it moves from one layer to the next, that advective flow is going to carry with it solids of a given concentration. So that's how we do, that's part of the mass balance term for any one of these layers, is figuring out how much flow is coming into it from the layer below and how much is leaving and going into the layer above. At the same time, excuse me, we also have the settling process happening. Now, this is different than the advective flow. This is really just, in absence of that flow moving around, it is the solids that are literally falling out of the layer above it into the layer below it. And so this is defined not by the movement of the water, but by the nature of the flux and the concentration of the solids. And this solid settling is the other term in this mass balance that is going through this whole system. So in each one of these layers, we can take a look at its concentration, and then we can figure out, given the model that we have, the settling velocity for that concentration. And then that tells us, multiplied by the surface area and so on, how much of those solids are going to fall down into the layer below. So for any layer, we calculate how much is coming in, how much is going out. Same thing on the liquid motion side. And then now we can calculate a mass balance. And then once we balance all of the layers, we will have concentrations for the whole thing. So that's basically what the models are. The key thing that we need to know is what is that settling velocity for the solids in that layer. And there are a number of different settling equations that are available in the literature and in wastewater textbooks. You can grab sort of any traditional textbook, and they'll probably have this one in there, the Veselin settling equation. And what it does is it describes the settling velocity as a function of the concentration in that particular layer of the clarifier. So as you can see here, when the concentrations are low at this end of the scale, the velocity is high, and then vice versa. So when we're in the very bottom of the clarifier where the concentrations are high, the settling velocity is low. Now, this is sort of a very simple representation. What we're using in GPSX is actually a much more sophisticated version. Oh, sorry, forgot to mention that in most models, they also apply a maximum bound on that settling. You can't go infinitely high settling velocity at very low concentrations. So what we use is a double exponential model. It's basically the same thing, except we're going to have two curves and we subtract them from each other. So we have the typical equation there, as you see, same as what I showed you on the previous slide. And then another one that has a different parameter. So it's the same thing, except we have one parameter representing the hindered settling, and one of them is the flocculent settling. So what we do is when you have these two curves and you subtract them from each other, you end up like this with this green line. And that's really the settling curve that we are after to be able to use in our model. So we're going to actually apply a couple of bounds on it as well. That's typically things that that is part of all of the GPSX one-dimensional models. Excuse me. We then apply this maximum settling velocity, as I mentioned in the previous slide. In this case, we don't want the settling velocity to be too high, so it'll sort of max out at that level, which you can set. We have a default value for it. And also a minimum requirement for settling to happen at all. So we sort of specify that there's a minimum concentration required for the solids to flock together and start settling at all. So there is sort of an area here, a small space at the very low concentrations where no settling will happen. So ultimately, it's this curve in green that is bounded by those two red lines that we're after. So I'm going to gray out that part of the graph, and this is basically the curve that we have that is the model in GPSX. This double exponential model, and there are two parameters up here, our hindered and our flock, that you can use to calibrate the shape and the slope of that curve to the settling performance of the plant that you're modeling. Excuse me. I think working at home here, I haven't done so much talking in quite a while. I lose my voice a bit. Right. Okay. So I want to talk about those two parameters because these are the ones that you can use to calibrate your model. So the hindered one, of course, is the one that controls what goes on in the bottom of the clarifier where the concentrations are high. So if you increase our hindered, it makes the thickening worse. So it kind of moves the lines in this direction. And as you can see, it actually makes changes to this end of the curve without making very much change to the top half of the clarifier, which would be this side. And the other parameter basically does it the other way around. The flocculent settling parameter makes changes to what's going on at the low concentrations, changing the settling velocity at different very low solids concentrations, while not really changing the bottom half of the clarifier. Now, in version 8 of GPSX, which we released last year, we added a new term as well for compression settling. This is for when you have very high solids concentration. So this is everything at the very far right-hand side of the system. And this probably could be its own webinar as well. So I won't have a lot of chance to go into it in detail today. But really what it's talking about is the fact that, excuse me, that you have a certain maximum limit of solids concentration that you get up to, and then the solids settling processes kind of change from being these gravity-driven ones to having many of the other things that would have otherwise been irrelevant become part of the relevant aspect of how fast you can get up to high concentrations. There are actually three papers that my colleague Rajiv Gold was focusing on when looking at the way that this part of the curve needed to be adjusted and made a little bit more sophisticated. And much of our work that we have done is based on this paper here in the upper left-hand corner, although there's also work by Ben Plaza and Elena Torfs also in this area too. So we've adapted much of that approach from there, where the shape of this curve, we go away from that double exponential settling curve into another set of equations once you get up to those very high concentrations. And you have the chance to calibrate this part of the curve too, if it happens to be very relevant to you. So basically, if you want to know more detail about the compression settling, just send us an email and we can go into more detail with you. Okay, so now we've got those parameters. They're actually typically very small numbers, like 0.00016, and they're not terribly intuitive. So the good news is when you are working with them in the secondary clarifier model, you don't need to address those things directly. What we've done, actually quite a number of years ago, is put in a correlation that allows you to set R hindered and R flock and V max, the maximum settling velocity, and correlated those to basically two more intuitive and understandable parameters, SVI and an empiric correlation, an empiric clarification parameter. So basically, we've now replaced having to fit a couple of parameters that aren't easy to really understand which direction you should go with ones that actually are a little bit more understandable. So particularly the clarification parameter, which is the one that controls what's going on in the effluent, it's an empirical parameter that goes from 0 to 1, which is from bad to good. And so you can adjust that in order to dial in your effluent TSS number. So the SVI basically calibrates the thickening part. It's going to calibrate what's going on in the bottom half of the clarifier, and the clarification parameter calibrates what's going on at the effluent, sort of in the clarification, the top half of the system. So when you go to the settling menu, there's a button at the top that's an on-off button. Basically, turn it on. I want to use the SVI settling parameters. And basically, I can use the sludge volume index and the clarification parameter now in order to set these up. This clarification parameter, it goes between 0 and 1, as I mentioned. Generally, I try to keep it within about like 0.2 or 0.3 up to about 0.8. I wouldn't go outside that. That tends to be a little bit too unrealistic, but something in there from 0.3 to 0.8 tends to be a good range to work in. The SVI number, you could theoretically take it from data that you might have. It is a very approximate correlation, so be prepared and be comfortable with the idea of having to pick that as a good starting point, but then make further adjustments in order to calibrate, then get those right underflow solids concentrations. Okay, so that's basically what the one-dimensional flux model is like. And the version that I've been talking about up to this point, called Simple 1D, does not have any biological or chemical reactions going on in the clarifier. You can then move on to a reactive settler. So you would select the Mantis 2 in most cases, because that is the biological model that is present in our regular library. And you have the Simple 1D model working in there, and then we basically overlay on top of that the biological reactions in each one of those completely mixed layers. So it's exactly the same equations that you would have in the aeration basin. We assume each one is completely mixed. We assume there's no aeration going on in the secondary clarifier. We do allow for oxygen transfer sort of out of the system. And say, for example, you're also producing methane or nitrogen gas or something, that would also be able to leave the system, but we basically don't have any regular sort of entrainment of any other gases. And you must source the clarifier to an aeration basin using our GPSX sourcing function, which you can find at the top of the window when you're doing your setup. And then it is actually very handy to use for denitrification and or other types, potentially hydrolysis of organics in that secondary clarifier. So if you know that that's going to be an important part of your system, I recommend using a reactive settler model. It tends to be a little more complex, so therefore it takes a little bit more extra effort to solve it when you're doing your simulations, because now, of course, it's like having 10 reactors on your screen on top of everything else. But it's all set up to be able to do that for you. Okay, so let's take a quick demo here. So let's go over to my desktop. And so this is GPSX, and so I've run a very, very simple activated sludge system here. And I just wanted to go through, of course, how you would typically take a look at using the clarifier model. And so I'm going to run a steady state solution to this particular system. So let's run 0 days. Let's click on start. And we'll let this come down. This is basically a really simple example from our sample layouts menu that's doing just carbon removal only, no nitrification here, I don't think. So in this particular system here, you can see that if I double click on the clarifier, it brings up this panel. That this is sort of typically the things you would look at when I want to be able to play around with this thing as far as getting it calibrated. So these are obviously all the results, and as you may know, you can switch this display up here at the top of the quick panel. This is sort of my preferred way of doing things, is to put this on TSS, and then now I can actually see the concentration of solids coming in and going out. So the concentration coming into this secondary clarifier, the mixed liquor, is about almost 3,000, and our effluent solids is 6.7. Our underflow solids is 5,800. So, that's sort of typical performance that we would get for this system. So if I wanted to go into more detail of calibration, this is a nice way to have all of those numbers up and easy to see and right there ready to go. If you open up this little panel down here a little higher and kind of scroll through these are other calculations that we're doing all the time, and they will be there available for you to take a look at as well. RAS solids, RAS flow rate, WAS production, and so on as a mass flow, the sludge blanket height, and other things that are available. I'm showing these in metric units here, but you can always just click on this and switch it to other things if you would like. So those are there available for you to take a look. And that's sort of a typical way of assessing the performance during that calibration step or whenever you're running simulations. Okay, so I'm going to go back to my slides and move on to talk about the important things you need to know when you're setting up your clarifier model. So as just like any object in GPSX, when you want to access the input parameters, you right click on the object, go to the input parameters menu, and there typically you'll see for most of them the physical menu, the operational menu, and the settling menu. Those are the three that you're probably going to have to visit when you're setting up your system. And when you're setting up the physical aspects of your clarifier, at the very top of the menu, the very first thing you have to decide is actually the clarifier type. And by that, we mean, what is the shape? And so here's an image from our GPSX technical reference. And you can see these are the different kinds of clarifier shapes that we have available. So actually, you'd be surprised. There's not all that much difference between the results you get out of the flat bottom versus the sloping bottom in terms of at least the way that it predicts. But anyway, you can choose whatever one you like. And then normally what you would do is you would enter in, the most important physical dimensions of the system, the surface area, the water depth. And if you had selected, say, for example, the sloping bottom version, you would go into this more button here, and then it would have things like depth at the center well, depth at the side wall, and so on, that allows you to define that slope and everything. All right. One of the important ones to keep in mind is this feed point from the bottom. Now, most of the things that you find in all of the GPSX objects that are on the physical dimensions menu are things that you would typically have an actual physical measurement for, like the surface area. So these tend to be things which have hard numbers and you don't normally play around with them a great deal. But this is an exception to that case. The feed point from the bottom actually is not intended to mean specifically the opening where the solids come in. It is actually the layer into which the solids will sort of come in and settle out in. And so therefore, it's actually not a parameter that is always directly measurable. And so it is one, though, that you can estimate to be something in the neighborhood of a third of the way up from the bottom of the clarifier. And it's often one that gets adjusted during the calibration step. If you put it at the very top or the very bottom of your clarifier, that actually won't work. You'll end up with very poor results. You want it somewhere in the middle, and you can move it up or down in order to be able to calibrate your model and get the overflow concentration and your underflow concentration into the right area. So as far as the operational settings go, there's going to be the top part of that menu specifying the underflow rate, or there's an option there to set up a proportional recycle. You have to specify proportional to where. You have to specify the label for that. Or you can have a straight up PID controller if you want to do something a little bit more sophisticated. Pump flow is actually the lower right-hand connection. This is normally where you would waste from. You can specify what layer you're wasting from. You can actually do that for the RAS as well. Or you can also set a PID controller here. Typically you could control mixed liquor or SRT from here. And there's some other parameters on this page for defining how you define the sludge blanket height, and also the various parameters that are involved in looking at the state point analysis as well. Okay, so moving on to the last of the three menus here is the settling parameters menu. As I mentioned earlier, we have that option to either directly adjust the settling parameters like R hindered and R flock, or you can turn on this correlation, which is what I usually recommend for most people, and use the sludge volume index and the clarification parameter in order to calibrate the settling properties of your sludge. One other thing that's available for you to be able to make adjustments to, if you like, is to look at actually this thing called a settling correction factor. Now, these are each of the individual state variables upon which we're doing our mass balance in our model. And you can actually make an adjustment here. This is sort of just multiplied onto the end of the settling velocity. So if you have some aspect of the system is allowing for one kind of solids to maybe preferentially settle out faster than others, XII, for example, here at the top, is particulate inert inorganic solids. So say that is sand or something that would settle out quite heavily and be quite a bit more preferentially settlable. You could actually increase this number from 1 up to, say, 1.1 or 1.2, and then you would note that you would see a change in the behavior of your system and get better settling, but it would do it preferentially to that one particular thing. That's usually the only place I ever come to visit this menu. If I find that my VSS and my ISS don't settle in the same way, you can come in here and bump this number up to get the inert stuff to settle up faster. So in this settling parameter menu, you'll note that the default values are different for each different type of settler. So this is the thickener, this is the primary clarifier, and that's the secondary clarifier. And you'll note, I realize these numbers are really small on this slide, but you'll note that the default values are actually different in terms of the settling characteristics of the sludge or of the solids for each of these three positions. So that's how we reflect, even though we're using the same underlying equations. That's why we have the three different objects available in GPSX. Okay, so I'm going to touch a little bit on being able to plot the kind of information that you need to be able to get out of your secondary clarifier model. So like a lot of objects in GPSX, you get different menus depending on where you right-click on the object. So if you click in the middle of the object, you will get the profiles of the solids or the concentrations of the individual components that we're modeling. And also the state point analysis graph is available by right-clicking here in the middle of the object. The other ones, the connection points for the two pumped. So this is usually we put RAS on the bottom and we put wastage, WAS on the side here. You can click there to go to the output menus and get access to all of the flows and concentrations that you would normally be able to get at any connection point in GPSX. And then up here, you can get that as well as a number of different specific clarifier models that clarifier parameters that we calculate and make available for you to plot as well. So for example, if I right click at that connection point and then I go to output variables and I go to clarifier variables, you'll see that we have a special menu there. And this is where you can plot, as I mentioned, sludge blanket height and layer thickness, the total sludge mass in that particular clarifier, and then ultimately that settling velocity and some of the other things that were calculated from the one-dimensional flux model that I mentioned earlier. Okay, so there are a number of different ways to plot the output that you need. Okay, so this one I already looked at and showed you in the previous example on the desktop there. You double-click on this, and then go up to that menu in the top right corner and switch it from flow to TSS. That's a nice way to get most of the information that you'll be looking for. The horizontal bar output graph is actually really fantastic. You can right-click in the middle of the graph, drag the solids concentration, the TSS concentration, up to a graph, and then select horizontal bar graph. What you're looking at here is actually the 10 layers, and then this is the concentration here on this axis. So of course, most of the solids are at the bottom, so we see the higher concentrations there. The grayscale output graph is actually basically the same thing, except it's done on a grayscale instead of left to right. And then also the state point analysis. And this is a whole full set of other calculations that we're doing in the back there. And state point analysis is a really nice way to sort of look at the flux in and out of a clarifier and then see where you sit with respect to the ability of that clarifier to settle out some solids. And this actually dynamically updates as you run your simulation, and this intersection point may move around. One thing I'll note, though, is the flux itself moves around too. So because it includes the amount of solids that are being lost in the effluent, you'll find that if the dot kind of drifts out here looking like it's going to get out close to where the clarifier might fail, of course the line moves out because as it fails, it's taking more solids out with it, and that goes into the flux calculation. So it's kind of an interesting dynamic way to apply what is normally a steady state type of analysis into this system. Okay, so I thought I'd do a couple of really quick desktop demonstrations. Okay, this time I'm going to run 10 days of simulation. And what I wanted to do is just show you a couple of those examples of the profiles. So let's run this. And what I'm going to do is I'll increase the flow rate here a fair bit, and you'll see the solids concentration start to come up in this clarifier here. as we go along. That increase happens as we come along in that system. So you can see the clarifier is starting to fill up because now we're pushing quite a lot more flow through that particular clarifier itself. So that's an example of seeing that sensitivity there. Of course, if I go to the effluent graph, you can see changes in the effluent solids and so on. Okay, so let me actually just go back and reset this, and I can reset my input. And here's a couple examples of the clarifier itself. Actually, I want to leave this at the higher flow rate to make the whole thing a little bit more sensitive. Okay, so I'm going to run a 10-day simulation here as well. Okay, so let's get that moving along. And I want to show you the difference of when I change that sludge volume index. So SVI, what that works, of course, is that if I move to a higher value, that means less thickening. It means I'm getting poorer thickening performance in the bottom half of the clarifier. So therefore, it's not the higher concentrations and layers up off the bottom of that clarifier. So I can see that if I keep continuing to decrease this, that the sludge does not thicken as much, or even the very bottom actually becomes less concentrated. And of course, if I go the other way, then I get much better settling sludge. Then we get really great performance at the bottom there. And the other one is to look at this clarification parameter. So this is the one that controls what's going on up here. Now this graph at this scale is not the best way to see this. So I'm going to move over here to this effluent graph. And so the effluent suspended solids is that black line. And if I change this, as I mentioned, it goes from 0 to 1. If I change this and make it better, we can see that concentration there in black start to come down as we get better quality of our clarification in the top half of the clarifier. We're removing more solids, coming down from 13 or whatever that was before down to 10 or less. So, and of course, if we go the other way, the other thing will happen. So, so these are parameters that you can sort of intuitively adjust in order to bring your underflow solids and your overflow solids into matching the numbers that you might have for your actual plant. Okay, so I'm going to go back to my slides now here. Okay. And just a couple of quick final thoughts about the clarifier models. If you are a user of our SBR models, sequencing batch reactor models, they are, as part of their cycles that they go through, some of the phases are for settling, and we use that exact same settling model from the secondary clarifier in our SBR model. So there's 10 layers there as well. They have the same type of settling parameters. I believe the same defaults as well. So the SBRs work basically the same way. The diversity of all of these different kinds of clarifier models, from the simple point settler all the way up to the more sophisticated one-dimensional reactive clarifier models that I mentioned. The reason we have all those different things is that you don't always need the most complex thing all the time. Sometimes it's actually really helpful to go with something simpler because I don't really need to have all of that sophistication around, settling velocities and so on. I just basically need to have something to do the job of getting the solids back into the bioreactor. So that's why we have all of that there. But the simple 1D model, which most people use, is really the best one for most typical applications. It's really good for steady state. It's actually, it can be done very realistically for steady state. When you're doing it in dynamics, you may find that a few things here and there need to be adjusted in order to make sure that it stays in good performance over a long period of time. But in general, it's the one that most people use.